Yeah.
Finer day and finer lecture. I was like pretending that like time was really fast. Like time was just very fast. Right? I mean, in the life, there's like some little goosey time and like few ends and time, and this is like one of those. And anyone remember where you guys are sitting on the first lecture, very first day? Everybody looked like very nervous. I mean, and I was, even though I'm not student, still make me nervous. So here we're starting the very last lecture of the school with here the final improvement of the 2D material, which is like at the heart of the theme of our school this year. So here's it.
Okay. So the plan today is talk about electron-hole double layer. The theme of the workshop is strongly correlated electrons, but I would like to step away a little bit from electrons and talk about the platform to study interacting bosons in solid states. So this is kind of my main goal. And if there's time left, then I'll go back to yesterday's lecture and finish the topological part. Sounds good? Okay. Yeah, so the system we study is something called excitonic insulator. And the purpose is to have a solid state platform for quantum many boson physics. So let me just explain, this concept of excitonic insulator to you. And this is not a new concept, as you can see, starting from the 60s, many giants in theoretical physics have already considered this concept. So imagine that you have a magical knob that can tune the band gap continuously. Okay. So let's take a look at the semiconductor side. You shrink the gap size continuously till you hit something, corresponds to the exciton binding energy. So that's the electron-hole interaction. So in that case, electron-hole pairs will be able to spontaneously form in your solid. So the density of electron-hole bound pairs, which we call excitons, is determining the balance of two different energies, right? One is the negative energy you save from binding electron-hole, and the other part is the repulsion between the bosons. So by tuning this knob, you can actually change the density of your boson. So in other words, you can control the chemical potential by doing this knob. Okay. So, and the threshold is when the charge gap becomes smaller than the exciton binding energy. And in a ground state, we expect to see superfluidity, this and that. So sometimes you can also call this boson-Einstein condensate, if you consider the semiconductor side. And you can imagine, this can occur also from the other side when you have a semi-metal, and this corresponds to the BSS limit. Okay. And experimentalists have considered many different materials, so over the years, we've been searching for candidates of excitonic insulator. Oh, by the way, so I call it insulator, so it's not insulating states for the excitons. Those are the insulating states for the charges, right? You can spontaneously form exciton can flow. So some small gap semiconductors or semi-metals over the years have been studied as candidate excitonic insulators, so I list a few, this is one of the latest. But in all those materials, electrons and holes reside in the same material. So it's impossible to establish independent electron contacts or hole contacts. And it's very challenging to directly measure or control those excitons. And it's also fundamentally difficult to have direct evidence to show that you have this excitonic insulating state. Because in solids, there could be other effects, breaking symmetry, you form gap, but whether it's due to, spontaneous formation of excitons or due to some other effects could be debatable.
So they are excited the charge.
So you cannot inject a charge into its charge incompressible. Then a couple of platforms, people studied in the past to generate excitons in coupled quantum well system. One is, a coupled quantum well, you apply a electrical field, you tilt the wells, and you optically excite electron-hole. And in this case, electron will spontaneously transfer to the other well, and then you have indirect, spatially indirect exciton. And this has been studied a lot in the optics community. The problem with this is that, those optically excited excitons usually are short-lived, and they recombine before reaching usually thermal equilibrium. So it's very hard to study the equilibrium phase diagram. Another example is also, two quantum wells, could be conventional gallium arsenide and other semiconductors, or could be graphene. You can turn on magnetic field, and each layer is half your lambda levels. So you can look at it, one layer is electron, the other layer is hole. So this effectively some kind of an exciton. So this has been studied experimentally by Jim Eisenstein, Philip Kim, you saw earlier in this workshop, Corey Dean, and in those examples, exciton binding is relatively weak, for example, in graphene, or in gallium arsenide, because, usually you cannot get the electron hole close enough. So the low exciton binding energy gives you a pretty small degeneracy temperature. So typically it's on the order of about 1 Kelvin. So we are searching for a new platform that can give you, for example, a large degeneracy temperature and also without a magnetic field. Okay. So I will mainly talk about, this platform that allows us to reach equilibrium electron hole on the zero magnetic field, and show you some thermodynamic measurements of the system to show that we really have an excitonic insulator, and then maybe show a little bit of transport results on excitons or even three-body bound states, which we call trion. And this is mainly the thesis work of this student. And I should also mention, there are similar studies of the same system from Fan Wang's group using the optical technique. I talk about the optically detected resistance and the capacitance on Monday. So ours mainly is just electrical transport. Yeah. Oh, well, so just give you a few examples, right? So optically, you can inject those excitons, right? And then they can study the property, whether you can, from condensate, look at the phase coherence, things like that. Okay, so we are talking about the equilibrium excitons. Yeah. Yeah. It's very difficult to reach thermal equilibrium. You excite the exciton and they need some time to reach equilibrium, and the lifetime typically is short.
Usually you can keep pumping to study exciton polaritons.
Okay, exciton polariton is a different issue, So let's just focus on exciton, right? So the question is, the difference between steady state and the thermal equilibrium. Those two are not quite the same. So you can keep pumping, keep the exciton density the same, and you can reach a steady state, but doesn't mean you have thermal equilibrium, right? And exciton polariton is an interesting topic, So there, it's not purely electron-hole. There's a photon mixed. So the nature of this polariton is pretty much photon dominated. So it's very easy in that case to reach, condensate states, like in laser. So with photon, everything is easier.
Equilibrium state.
Yeah, thermal equilibrium. Yeah. No, you don't need to pump. Yeah. But you can pump once and then let it evolve, reach thermal equilibrium.
If it doesn't form.
If it doesn't form exon insulator, if they do not recombine, you can, so let me put it this way. Maybe you wait a little bit to see what this is. Yeah. Okay, so I'll get to your question here. Okay, so this idea, comes from Alan McDonald's group. I just listed a couple here. So imagine that you can put two monolayer semiconductor, for example, the transition metal dichalcogenides I talked about yesterday, very close to each other. And then if you can manage to put the electrodes on each, like what I'm doing here, and you can apply some bias, let's say. So, without this bias, you have band alignment like this, so we can pick two materials with this type 2 band alignment, which means the conduction band, the minimum, and the valence band, the maximum, reside in two different materials. And this EG is the band gap. It's an indirect band gap. And if you don't do anything, the Fermi level is in the gap. Now, if I apply finite bias between those two layers, you split this Fermi level into two, electron and a hole, and this is controllable, right? So now the effective band gap for this system will be EG minus this value. You're with me, right? So as soon as this effective is smaller than the exciton binding energy, you can spontaneously form those excitons. So let me get back to your question. When you first turn on this voltage, there's short period of time, you have electron-hole injected, right? And once you reach this density, then it will just stay there as long as there is no tunneling between the two layers, no recombination. Yeah. Yeah. Yes, exactly. Yeah. Okay. So in this case, this carrier density is determined by how large the bias I turn, right? And this can be continuously tuned. And that means I can do a thermodynamic measurement because the exciton chemical potential is pretty much determined by this voltage, chemical potential or density determined by this bias voltage, right? And I can electrically control exciton transport if I put more contacts along the two layers, right? So they can flow. And we can also get into the regime, the excitons can strongly interact with each other. You know, if you design your structure right. And if the density, the disorder density is low enough, temperature is low enough, the ground state should be superfluidity. What I mean is that you should reach interlayer phase coherence, and you should have dissipationless currents in the counterflow. Yeah. Yeah. Yeah.
So when you talk about the exciton transport, is this like that the one exciton I just created is moving point A to point B?
Exactly. Yeah.
So then what make it move?
Oh.
Some diffusion, or I mean, it's charged neutral, right? I mean,
Exactly.
so what do you mean by electrical?
Yes, yes. So, you know, imagine that I can always drive electron current, right? And then because of the electron hole binding, the hole will just be dragged. It will follow. So
Dipole and the rotate, and then just
the
part is like,
so you have an electron current like this and a hole current like that, right? So it's like the electron and the hole move together. That's what I mean.
so that's not directly, you know, like the field was applied to exciton. It's just the kind of secondary effect. Of the
No,
electron
so you can drive currents, you know, for example,
One
you need to have bias in one layer. Yeah,
I see.
Yeah.
So only one layer bias independent of the EVD.
exactly. Yeah. And I'll show you some examples. Oh. Oh, yes, yes, yes.
So they can,
Exactly. This is a very important. Yeah. So the spacer, usually we just use HBN. You know, you can imagine some kind of a vacuum for us, right? And the purpose of the spacer is to make sure that, you know, those two layers are Coulomb coupled. There is no tunneling. And this is very important. If you have tunneling between the two layers, if the tunneling is not negligible, then this is not going to be thermal equilibrium. And this is a case similar to optically excited, they recombine, right? How do we make sure of that? You know, yeah. Experimentally, what we can do, we can increase the separation between the layers because tunneling is an exponential function. And we also make sure that this layer and that layer, in terms of the crystal orientation, they are misaligned. So it's you know, makes it's even harder to tunnel. So you can measure it directly. Well, in practice, there's always something, right? If you can, you know, measure well enough, but you make sure that this tunneling is negligible to something, you know, so the something will be this in plane. And you can also measure the kind of the lifetime. It's like an RC lifetime, right? If this is a much, much longer than all the relevant time scale, then this is okay. Yeah. Okay.
In this picture, should I think about bandage coming closer and then it's spontaneously forming the exciton, or should I be thinking I'm injecting electrons and holes and they form?
Okay, so it's not the band edges that becomes, you know, so they stay unchanged. So that, no, you're thinking about this edge,
Yeah.
they don't change.
So you're,
When I just apply the bias.
so you're literally injecting the
Electron hole.
Yeah, doping the system by general bias.
so these are interlayer excitons, right?
Exactly.
Is it possible that you also find intralayer excitons here?
Because we are doing electrical injection, you know, you only inject the electron here and a hole here. Of course, you can also do intralayer exciton by optically excite.
The exciton here
Yeah.
is stable, steady state limit.
Also, and they also can reach thermal equilibrium. Yeah.
Is the thermal equilibrium drop like throughout with the electric bias, and they are still stable?
No, you need this, you know, so this is just like a, think about this, if you have a capacitor and you have electrical field, right? And, you can write down the thermodynamic quantities. So this is thermal equilibrium.
And the transport you're mentioning, is the counter flow?
Yeah. So wait a little bit, I'll show that. Okay. So I showed you this picture yesterday, so there are many materials to choose from, and we just need to come up with something, with this type 2 band alignment. And in this experiment, we're going to pick a moly selenide and tungsten selenide. And this is just for practical reasons, not, as long as you have the proper band alignment. We also want the indirect gap to be not too big. Otherwise, you will need to apply large voltage. Okay, and so the reason why we pick those semiconductors is because the strong exciton binding energy I already mentioned Wednesday and yesterday. And I explained the reason why, because of the reduced dielectric screening. So experimentally, we have measured this binding energy. It's on the order of half electron volts. So this is very, very big if you talk about exciton binding energy in semiconductors. So in gallium arsenide and other conventional semiconductors, we are talking about something at least 10 times smaller, even more. So order of magnitude is different. And this exciton binding energy is from, the fundamental exciton resonance to the band edge. Okay. So what are the implications for large exciton binding energy? I already, yeah.
Most of the materials you showed, is the interlayer band gap a direct band gap, or do you have finite Q pairing?
Oh, so you mean if I pick this and that, or?
Okay, they both at the gamma point?
No. So those would be like, we usually purposely misalign the two layers, so they are not correlated. So it's not too relevant to talk about, whether the momentum, yeah. So they are spatially indirect. Somebody already asked this. So I already mentioned this, the reason why we pick those instead of graphene is to have large degeneracy temperature. So we can just do a very simple, hand waving argument, so the degeneracy temperature for 2D is linearly proportional to the density. So the higher density you have, the larger degeneracy temperature you can have. So what is the largest density you can reach? When you put the two excitons, very close to each other, they will ionize. And this is something, we call it exciton Moore transition. So it's different from the Moore transition we talk about for electrons, metal insulated transition. So this Moore transition is when the two excitons are very close to each other, they ionize. Okay.
What is the speed? The temperature of the
okay. So I probably should have give you a little bit better introduction. So let's consider non-interacting bosons first, right? So in 3D, I don't have to be in 3D, right? So there are two length scales. One is the interparticle spacing, right? And the other one is the de Broglie wavelength, right? So when the interparticle spacing is smaller, or in other words, when the de Broglie wavelength is larger than the interparticle spacing, then a large fraction of those bosons can condense into the ground state, the condensate states, right? So this is for 3D. So in 3D, the density, it's a different power law, right? But in 2D, it's linear. But of course, in 2D, we do not have long-range coherence, and you need to cool further down to BKT temperature, to get to that. So, so this is just a kind of upper bound you need to consider, the degeneracy temperature. And this is the temperature when the de Broglie wavelength becomes larger than the interparticle spacetime. So what is the maximum density you can have? That would be, the density you reach, which we call the Mott density for the excitons to become electron-hole plasma. Okay, and it's the work of the same Mott. That's the problem when somebody is too productive. You have names as this and that. It's kind of confusing. So we can sort of rewrite this. The maximum density is related to the bar radius. You say, 2 bar radius or 3 bar radius, and they ionize. So that's this numerical factor. And from those papers, so this factor will be 0.5, 0.3, something like that.
If they come too close, they can crystallize.
They can what?
They can crystallize, right? These excitons.
They
Form a solid state, like an exciton.
No, when they're too close, it's like you are seeing the internal structure. So it's no longer a bind exciton. So you become electron plasma.
But does it go directly from an exciton superfluid to a plasma, or is that?
Oh, this is a very interesting question. I think, both theoretically and experimentally. We'll see a little bit what we can do, but we cannot fully answer a question like this. Okay, so if we this binding energy I talk about, the half electron volts, and that will give you something huge. And this is one of the motivations to go with something like that, right? Because if you consider 3D case, when you have a dilute, non-interacting both gas, this temperature we're talking about, is very close to 0 temperature. Okay, so this is good and works in our favor to get perhaps room temperature exciton condensate, right? But on the other hand, very strong light coupling, that's something automatically from the very strong exciton binding energy, right? But if you have very strong light matter coupling, that means your radiative lifetime is short. And if I put in, this half EV binding energy, the lifetime is on the order of picoseconds. And this is not going to work, right? And this is why we put, electron in one layer, hole in the other layer, and with some dielectric spacer, typically on the order of 2 nanometer. And this 2 nanometer is chosen that, the electron hole binding is still sufficient, it's still pretty big, but on the other hand, the tunneling, you kill radiative and even tunneling between the 2 layers. So this is kind of the optimal distance between the 2 layers. And of course, the binding energy drops. So depending on the thickness of the dielectric barrier between the 2 layers, the binding energy drops from, a couple of 100 millieV to, for this case, on the order of 20, 30 millieV. And all those things can be directly measured. And I'll show you an example how to measure it. And, so our group, Kim and Fang's group, so we experimentally realized that this platform for some time. On the right hand is just a very simple calculation by Michel Faulkner and the collaborators. They consider exactly this problem, when the 2 TMD semiconductors are 2 nanometer away from each other, and they look at the phase diagram, temperature, and the pair density. So when you increase the pair density, you reach, so this some limit on the order of 10 to the 12 per centimeter square. This is the Mott transition I was talking about. Exciton will dissociate, become electron-hole plasma. And this dashed line is that degeneracy temperature, talk about when the de Broglie wavelength becomes comparable to the interparticle spacing. So in this red area, we're talking about quantum Bose gas, and above we're talking about classical. Yeah.
You have a dipolar exciton, have a dipole. The density is high enough. It should be good.
Okay. When the density is high enough, excitons do not exist anymore. So all this we're talking about the low density limit. This is, yeah. Okay, and then, if you have a higher temperature, you can thermally dissociate the exciton. And then this is the BKT transition temperature. And only below this, we expect to see superfluidity, phase coherence, things like that. Okay, so this should be our guide, but in experiment, it could be a little bit different. Okay, so let me just show you the device structure schematic. And you have seen this before. We want something that can control quite a few different things. So I already explained this bias between the two layers. And you see that the channel where we're interested in low density exciton is a little bit different from the contacts. And the reason is because from ohmic contact, or at least, low Schottky barrier contacts. So we want the doping density in the contact area to be large, very large. So then you form good contacts. But in the channel where we're interested in the problem, the density is very low. And to achieve this, we have top and the bottom gates. And again, we have two gate voltages, right? If those two are symmetric, you can think about, the symmetrical part, which will be this VG. And the anti-symmetrical part will be this delta, and which gives you a displacement field. So in other words, all those different layers are at the different potential already if I have this delta non-zero, right? And now, what this does, get back to your question, you put those two layers at different potential. So effectively, you already reduce the gap size when you just apply this delta. But now the contact is at the larger potential difference because they are further away. So at the contact, you already invert the two, so you can, heavily dope the contacts. But in the channel, this gap size is smaller than when you just put the two layers together. So in the experiment, I'm going to show you, we reduce this gap from 1.6 EV already to 0.6 and 0.7 EV. Yeah. You mean here? Yeah. They should be homogeneous, but forget about this tiny area. What?
So, but if the field is homogeneous, how does the density become?
No. Okay. So if you look at the middle, this should be homogeneous. If you look at the edge, should also be, but there would be some, edge effects when you consider somewhere near here. That's why I didn't try to draw the density profile, So if you look further away from the edges, it's okay. Okay, and so I already mentioned that this EB will split electron-hole chemical potential, right? And this VG just to shift the two chemical potentials together up and down. And effectively, we are doping the system, either dope electron or dope hole. So there are a lot of controls in this experiment. First, let's look at the electrostatic phase diagram. As the two voltages, the gate voltage and also the bias voltage. And this is a simulation ignoring electron-hole interaction. So when the bias voltage is small, we can have intrinsic for both layers for small gate voltage. But then if you tune the gate voltage, you can become electron doped and hole doped, right? So on this side is hole doped, on the other side is electron doped. And you see this triangle is not like this, what you would expect to have is because we ground, the tungsten selenide layer. So this layer is grounded. So that's why the band edge of one of the material doesn't move, and the band edge of the other material change linearly. And then if you apply a large bias, somewhere here you can see already, even if you don't apply gate, you can put hole and electron in both layers. So this is a kind of the electrostatics for the system. So now we would like to measure the exciton properties. Okay. Yeah, so that's the alignment of band. Okay, so the first thing we want to do is to look at the charge compressibility. Remember, our goal is to show that we can inject electron-hole pairs, and we cannot inject electron or hole. And this together will show that we have an excitonic insulator, right? Okay. So let's take a look at the charge compressibility, and we do capacitance measurement. So in the setup, we put a small AC voltage on top gate, and we measure the induced charge at the bottom gate. So if one of the layers or both layers are doped, then the electric field from the top layer will not be able to penetrate through to induce charge. So in that case, you just get zero. And when you get the zero, that means it's metallic, the two layers. And then when it's insulating, then this is not zero. So this is the expectation. And this is our measurement for the case when we just put bias at the zero. And it's not strictly zero when it's doped. And that's because, the device is imperfect, not perfect. You can have a small area of monolayer sort of not perfectly aligned between the two. So they are outside of your area sort of, but reasonably good. So at this voltage, it's the constant selenide band edge, and then you have a moly selenide band edge. So from here to here, the double layer is insulating. And this distance also tells you the gap size, right? Yeah. 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 It's different in the idea is the same. It's just that where you do the measurement. Last time I talked about take a current induced here, but now we are taking current here. So this is something called the penetration capacitance. Okay. And then if you do the measurement for all V bias, you get something like this. And this is fully expected, right? Red means that the system is charged incompressible. This means you have insulator. So only when both layers are insulating, you get this red triangle. And outside, at least one of the layers is doped. So the penetration capacitance is very small. Okay. So the next measurement we would like to do is to look at exciton compressibility. And the way we do it is to apply AC voltage on one of the semiconductor layer and try to measure the current induced on the other layer. So the current has two components, the real part and the imaginary part, right? So the real part of the current is the tunneling, so that's something we can measure. And then the imaginary part of the current, we call the displacement current, is proportional to the density. And this ratio is the interlayer capacitance. And this, if you look at it, I already mentioned this voltage, bias voltage, is just that the exciton chemical potential. So effectively, this interlayer capacitance measures the exciton compressibility. Okay, and this is one of the curves. Let's look at the black curves. Okay, black curve. I already normalized by the geometrical capacitance between the two layers. So initially you have nothing. That means we cannot inject the exciton when the bias is very small. Then when it hits this threshold, 0.6 some EV, immediately the compressibility shoots up. And that means now we can inject exciton into the system, right? And then when you inject them more and more, when you move to a larger bias, this value goes to 1. That's the geometrical capacitance, what we expect. And then we can integrate this curve, become this red curve. And this, with this, you see that you get the density out. So that's on the right axis. So by applying something like a 0.1, 0.2 volt, we can inject, 10 to the 12th centimeter square per centimeter square excitons into the system, and it's a monotonic dependence. We can also look at the compressibility as a function of density at different temperatures, and you see that it's sort of start with a linear increase and goes through some kind of peak and then goes back. When you get higher density, it becomes 1. So this kind of a nonlinear behavior of the compressibility as a function of density already tells you that there is interaction between the excitons, and then of course you can come up with some many-body boson model to describe or explain what's going on here, and then extract the exciton interaction energy. Yeah, so if you think about compressibility of exciton, there is low temperature limit and a high temperature limit. So I probably should have plotted this differently. Instead of as a function of density, I should plot it as a function of at the fixed density as a function of the temperature. So if you do that, this will be mostly kind of a linear, and then you get, for high temperature, it goes linear with density, but then there will be a departure from that, it doesn't hit 0, but it hits something, and that something is due to exciton-exciton interaction, and that's the interaction. This?
Yeah. The black.
Yeah.
Why does it shoot up and down?
Oh, so this is the point when you start to inject. So you get exciton in. So the question will be like, why this is larger than 1, not 1, and that's due to interaction, Yeah. And I can send you some. Well, you can take a look at the 2 papers I cited from Alan McDonald's group.
There's no phase transition.
No phase transition. It's the same electron density, and the hole density is the same. I didn't mention this, so this is measured at a certain gate voltage when the electron hole density is the same. No, that's something I don't know. So this axis if I want to be more accurate, should be pair density. Whether they are bound or not, we still need to look at it. So this is just the pair density. So at the small density, it's bound. But at a large density, you just add electron density and a hole density. Okay, so now the question is whether we have only bosons or both Fermi mixture, right? So in this case, I make the electron hole density the same, so it's not a both Fermi mixture. So if they form exciton, you just have bosons in this case. But what you said is something interesting to study, right? Use this as a model to study both Fermi mixture. Okay, so now let's put everything together, right? So this is just a simulation ignoring electron hole. And this is the penetration capacitance that measures the charge compressibility. Remember, the red triangle is from charge compressibility. You have, insulator in both layers. And on the right-hand side is the exciton compressibility from the interlayer capacitance. Red means you can inject the exciton, and the blue means you cannot, right? So let's compare the two carefully. So I draw those two dashed lines, right? So this dashed line tells me that I can already inject electron hole into the system, right? But this means, in this phase, the two layers should be insulating, right? So what this tells me that in this triangle, the tip, this triangle, I have excitonic insulator because it's charge incompressible, right? You cannot put charge in, but now you can inject the excitons. So this is the excitonic insulated phase. I hope you are convinced. Okay. Rest part. So here you go back to the picture that, let me. So there you just have something like this, right? So the chemical potential are split, but you don't have either electron or hole, and you also don't have exciton. Does it make sense?
So just to check the colors.
Yeah.
The part in the middle, red would mean
This?
right. So red color would be is incompressible for injecting electron.
Yeah.
And on the right, red is compressible for injecting exciton.
Okay, so yeah. So maybe you just don't like my color scheme.
Sorry,
Okay. So I'll let you look at this more for a couple more minutes. Okay. So let's get back to this. So inside this red, that means I cannot put either electron or hole, right? And in this case, I use the color red. That means I can put electron or hole. Okay. Sorry. And you remind me, I didn't mention that, from the separation between those two lines, I can read out the exciton binding energy. It's 25 millieV in this case. Okay. Yeah.
Not floating like this, what happens? Back the you can write down the total capacitance, the geometric capacitance with the one.
Okay.
You subtract the geometric part. What do you get?
Oh, so you're talking about the charge part? Yeah. Yeah, so if you subtract it, you get this part. Yeah. Right. And so it's normalized to 1. Okay, So let's just put this phase diagram together, right? What's interesting is this red triangle. We have excitonic insulator. You can put electron hole pairs in, they are bound, but you cannot put electron or hole into the system. And this bottom, you ask, so this is no electron, no hole, no bound electron hole. Right? And this side, you only have a hole, and this side, you only have electron, and the rest, you have electron hole, they are now bound. Okay, and then this dashed line is the configuration for electron equals to hole. Okay, and then we are going to examine what happens, along this line. So let me get to this phase diagram. Yeah.
So just a follow up on this question. So in that small red triangle,
yeah,
this is saying that because you can't inject in either electrons or holes, the condensate fraction is 100%.
Let me put this way: 100% at the zero temperature, 100% are in electron hole bound states. Yeah.
But then above this in the gray region,
okay,
can you still have some excitons, but
no,
also have mobile electrons?
Okay, so at this tip, I should mention this. So the exciton binding energy, remember there's screening effect, right? Is not a constant. At this level, the exciton density is very low. You have the largest exciton binding energy. When you turn on the B bias more, you have more and more excitons. The exciton binding energy drops. And then once you reach that tip, exciton binding energy goes to zero. Yeah.
Going red to gray,
Exciton Mott transition, exactly. Okay, so let me just show you the phase diagram in the special case when electron and hole density is the same along that red line. Okay. So what I'm plotting here, temperature versus the pair density. And on the right, I just give you this schematic, simple calculation, from Fogler's paper as a guideline. So the color means the exciton compressibility. So first, let's look at this black squares. And the black squares is the exciton ionization temperature, which we measured from the charge compressibility. So this is some kind of a crossover from exciton to electron hole plasma. So that's this line. And then this dashed line is the estimated degeneracy temperature, just based on the density. And then this black dots are the ones, I show you how the compressibility changes density at those peaks. And that peak actually tells us, when the exciton-exciton interaction sort of becomes comparable to the thermal excitation. So you can see that this slope is higher than that. And kind of rough estimates, you have a difference on the order about 5. So this actually tells us about the interaction energy between the excitons. And in this dimensional exciton interaction times the density of states, this is on the order of, is it 5, I think, or 10? You can check that paper. I don't remember exactly that number. And we also made an estimate compared to helium, and it turns out to be 10 times bigger than in the case of helium. So this tells us, the system can be engineered to be strongly interacting. And let me get back to your question of what's happening here, right? So, and this is the tip of the triangle. You can read out the density of that tip and look at the exciton binding energy in the limit of very low density, or you can convert to Bohr radius. And this factor is 0.4. And I remember I showed you earlier from the theoretical estimate, this is something between 0.3 and a 0.5. So on the ballpark, it's consistent. So, you know, when the density becomes this level, we have exciton insulator to electron hole plasma transition. But here is some kind of a crossover at a finite temperature. So compared to this picture, sort of captures the main feature, but you know, a lot of details probably need to sort out.
Zero temperature, is it a first order transfer?
That's a good question. I'll get back to that. This actually is topic on the debate. And this measurement, of course, cannot tell you too much because, you know, it's still at the 10 Kelvin. And this is at the time we still struggle with the contacts, you know, 10 Kelvin was the lowest that we can measure. So I'll show you lower temperature measurements. Okay, so I hope I convinced you that, you know, from the thermodynamic measurements, we already realized this excitonic insulating phase. So now I want to talk a little bit about transport. How do we do this? So the first configuration will be this drag counterflow measurement. So what this is, you know, we just, in one of the layers, we put a bias, and then you can drive current. And in the other layer, we just hook up to an ammeter and measure what the current going through there, right? So if electron hole are bound, then we expect them to move together. So in that case, you know, we should have perfect drag. What I mean is that this drag current should have the same amplitude as the drive current, but opposite direction, right? And then if they are now bound, then you just have, you know, electron hole plasma at low temperature. You don't expect to have current in the other layer, but this will give you, you know, small frictional drag due to Coulomb interaction between the two layers, and that will give you T-square dependence.
So that's a Coulomb drag.
Cool, yeah. So let's take a look at the measurement. So this is already a different device. Again, you know, in this black dashed triangle, this is the excitonic insulating phase, right? So now if I drive one layer, so in this case, I drive the electron layer, and you see current showing up when the electron layer is doped. So when you see N, then the red color shows up. And when it's I, that means no current. So the current is proportional to doping density. And it's not perfect, as you can see, you know, like near the edges, you know, you always have some defects, things like that. So this boundary is not quite right. So now if we measure the drag current in the whole layer, and you see that you get the current only near inside either this excitonic insulating phase or near it, right? And this is what we expect to see, you know, the drag ratio should give you 1 if it's excitonic insulator. So let's take a line cut here. So this is one of the line cuts. So the black curve is the drive current, and it turns on when, you know, the material becomes doped. And you have some kind of noise here. This is due to imperfection in the device. It's not, you know, and when you warm up or you change to a different device, you know, those wiggles are not there. Okay. And then you measure the drag current. It follows this drive current until you hit some density, and then it drops. almost to zero at low temperature. And if you compute the ratio, it's perfect. It's 1, right? And then after this density, it drops to 0. And this, again, is your Moore transition, right? Just to convince you, so this magnified by 100% is the tunneling current. And you can see that this is way below what's going on in the system. And this actually is required to have valid counterflow measurements. You are only in plane, nothing is out of plane. Yeah.
How large is what is your code?
Here.
No, I mean, compared to the quantum Hall bilayers.
Quantum Hall bilayers. So there, the situation is a little bit different, So in the quantum halls, they also have a edge current, and they need to tilt their magnetic field a certain way to kill this, So in our case, and there are also different devices. So I wouldn't compare like whatever the number I read out from here to their device,
These are DC current?
This is a small, very low frequency. Yeah, so, yeah, so let me just move on. And then if you switch the row of 2 layers, you should have the same exciton current, and that's what this is. So it just, convince ourselves again, this is real.
So if you increase the drive current, is there any critical drive current above which?
We try to keep this low as possible. That's, yeah. Yeah.
Why was there like disagreement between the transport and the capacitance measurements when you go like to the left or to the right of the triangle?
Oh, okay. So, yeah, so if you're outside the triangle, you're talking about here, right? What's going on? So there is no drag or very small drag except, somewhere here. And I will talk about those a little bit later. Yeah. Yeah.
In that region, all the electron holes still band each other?
So here, electron hole are bound to each other. Yes.
But in the mode, like in the mode phase, it's like decoupled electron hole?
In the Moore case, above, you mean here?
Yeah.
Yeah. Electron hole, and you have frictional drag, but they are very small.
So they start coupled.
They are, yeah. Okay, so let's take a look at the temperature scale. Don't want to get into the detail, So it shows that, roughly somewhere 10 or 20 K, still pretty good, perfect drag. But then, of course, when you go to higher temperature, you can thermally also dissociate some part of the excitons, so this goes down. And this compared to, the gallium arsenide, the double layer quantum system in the quantum Hall regime, it needs to be cooled down to something like sub-Kelvin in order to see perfect Coulomb drag. So this again shows the different energy scale. So this is a much larger energy scale. Exciton binding.
Yes,
Oh, okay. So they are about 2 nanometer apart, electron hole.
But I really should the XY point.
Yeah. Yes. They are tightly bound, if that's what you mean. A few nanometer in size.
How does frictional friction does it?
As a function of density, I think it increases.
Here, relevant scale is like the 25 MeV of the
Yeah.
system binding energy.
Yeah.
And so for more system that's a lot smaller, I mean,
Oh, you mean that this scale is still smaller than the 25 milli EV?
no, but in quantum Hall,
Yeah.
system, Electron well system.
Yeah.
You have to go down to 300 millikelvin.
Yeah.
So that implies that, you know, the binding energy is like a lot smaller. I mean, because solar fluctuation break the pair. That's
Yeah,
why.
yeah. I think in the quantum Hall system, it's a little bit of, I feel like the picture would be slightly different because there, you know, there is those edge states, you know, how they couple. So effectively, I think the electron-hole interaction is much weaker than the 25 millieV in our system. And how to translate this 300 millikelvin directly to the binding, because there is also, it's like transformation, right? Because in both layers, they have electron, but you put it at a half field lambda level and you transform this into hole. It's charge hole transformation also involved. Yeah.
Use like high density and low temperature friction gravity to permeate.
Yeah, yeah. But this.
Yeah. And when does it turn over? Like what's at the temperature?
Goes back to what?
Then it decays, right? That.
Yeah.
Yeah. So what happens? It's not a liquid.
No, it's still a pretty good Fermi liquid. We don't quite understand why there's non-monotonic behavior. Yeah. And I think, you know, this circuit of how we flow, how we drive exciton, like potential drop here and there, those are the things need to be considered more carefully in order to analyze this. So this I just to show you, you know, there's this temperature scale, but detailed dependence on density or on temperature needs to be carefully modeled. So now this exciton binding energy, you know, the mole transition, right? It's right here. So the question you raised, you know, is this first order phase transition or if it's some kind of a continuous phase transition? I think lots of theorists consider this as some kind of abrupt, right? So let me show you what we found in this experiment. And, you know, so this measurement is not super sensitive. So we want to turn into some resistant measurement. So let's look at this different configuration, drag resistant measurement. So in this case, we just open circuit in the whole layer and we drive electron layer. And then the resistance, you know, will be the voltage developed on that open circuit divided by the drive current. If we just have electron-hole plasma, then we said it's a, you know, Coulomb, the frictional drag, it goes like T square. And then this is how it looks like. So we change the VB, which changed the pair density. So the blue are for low pair density and the red is for large pair density. And you can see that, you know, for blue, it's insulating behavior, right? At a low temperature, the resistance is bigger. And this is consistent of having bound electron pairs, right? If you move only the electron, but try to move electron, but since hole cannot flow, you have an open circuit, and that gives you large resistance. So this is expected. But for high density, you know, we expect to have electron-hole plasma, then you should have metallic behavior. So this is the T square dependence. And we can try to, so then this is the phase transition between, you know, it's an insulated to metal phase transition. And we can analyze this T square dependence. And this is how it looks like. So this is the density when we have insulator to metal transition. And this T square goes, you know, as this open symbols. And if we try to fit it to some function, it goes like density, but, you know, renormalized from that Mach transition to the power of 1 -3. Okay. So, this diverging behavior perhaps is a good indication that we have a continuous phase transition. Right? But why, this coefficient goes like this density, but shifted by from this mod density to the -3rd power is still something, we don't quite understand because from frictional drag, this A coefficient, from those papers should just go like the total density to the -3 power. But now it looks like it's counting, not, but counting from this. So that's something, still needs to be considered, studied. So I think we have some evidence of continuous mod transition. Unlike many theories predict this is some kind of, well, either crossover or something more abrupt. Yeah.
Sorry, what is NPN and
Oh, okay. So this is the pair density, right? And NM is the mod density. Oh, mod density is the critical density when electron hole becomes unbound. Yeah. Oh, this N mod? No, this depends on the binding energy to spacing between the layers, right?
you showed some relation that NM times AB square is equal to 0.4.
Yeah, sort of similar, yeah.
Just to be sure,
Yeah.
when you go from like beyond the mod transition,
Yeah.
you immediately see the drag ratio goes to almost zero.
Yes,
But
at low temperature.
But here is as if also continuous because you have this fraction that.
What is continuous
So
here?
you are saying this evidence of continuous mod transition at N mod.
Yeah.
But also the drag ratio is a abrupt jump.
Yes, from the experiment. Yeah.
Like the feeding to that formula
Yeah.
works better away from the critical point, not near the critical point.
That's
Is
true.
there, like, further effect?
That could be, and also, the range of, if you go back here, so the range of t square also smaller. So the error bar is bigger. Okay, are we good? Okay, so I think I don't have time to talk about the other topic, so let me just finish this. Okay. So far we have studied just the boson system. Right? The system also has the capability to dope it. So let's say you go a little bit this way, you add a little bit of hole into your excitons, and you go a little bit that way, you get electron into the system. So this is a good platform to study both Fermi mixture. Right? And even more exotic states, for example, 3 particle bound states or 4 particle bound states or 5, just use your imagination, whether those guys can exist. For example, I'm just showing a 3 particle bound states. And this is something, in optics or semiconductors, people call it exciton. So excitons are pretty well known in optics, when you optically excite, dope the semiconductors, when the doping density is relatively low, you can think about forming some kind of a 3 particle bound states. And in many different materials, they have been seen. But tryons in thermal equilibrium has not been seen. So this gives us a chance to do that. Okay, so the measurements, I already talked about, we drive current in one layer and open circuit in the other layer, and we measure the resistance in the other layer. And that resistance is sensitive to interlayer Coulomb interaction, right? We already saw. So again, this is the capacitance showing the front faces. And this is the resistance measurement in the open circuit geometry at 1.5K. And you can see already, something is showing up here, right? But if I cool it down even more, and you see this feature coming out. So not just the inside the triangle, it's insulating because, if you open circuit the whole layer, you cannot drive current pretty much in the system, right? And it also happens, along this feature. And what this feature is actually is exactly when P equals to 2N. So we have 3 particle bound states here. So now I would like to probe along this line when we have the 3 particle bound states. So here is the resistance as a function of the 3 particle bound state density. For small density, we have some kind of an insulating behavior. And for large density, we have some kind of a metallic behavior. So this, again, reminds us of what's going on with the excitons. Okay. And then indeed, if you analyze the temperature dependence, you can get, the activation or whatever, estimate the binding energy of the trions. So at the 0 density, the binding energy is the largest. In this case, about 3 milli-electron volts. And when you increase the trion density, continuously goes down to 0. Yeah. Yeah. Oh, okay. So let me just farm this. Okay, so let me go back to this. So let's say we drive electron, right? So and this is an open circuit. If those 2 layers are independent, then I can flow the current, no problem, right? But if the particle here and the particle here form some kind of bound states, then I cannot flow this current, and we'll get a large resistance. And large resistance corresponds to some kind of a bound interlayer states.
Why variant has a higher resistance?
Oh,
because it's still electrically charged, the fermion, so.
Because, yes, because they are bound together. So I'm flowing electron here, but the holes here are in open circuit. They are not allowed to flow because the circuit is open. So that means electron cannot flow. Yeah. Yeah. So you will get, so the value could be different, but behavior would be the same, right? So if I flow hole here and leave that guy open, then I also get a very high resistance state. That's something we haven't looked at very carefully. Most likely, but there's also contact resistance, things like involved. So it's probably hard to directly compare the numbers. Insulator, yes, yes. But how large the resistance, also depends on the contact resistance on the. I think that's something probably is true, but we have not done the experiment. Yeah.
Sorry, one more. Yeah, so here, why? So I would imagine once you go right-hand side,
yeah,
it will be drastically.
It's log scale.
Oh, it's okay. So it's still kind of insulating, right?
No. It's a metallic because so this is a high temperature.
Oh, I see. Okay.
It's flipped. Yeah.
It seems like there's only something with clear features to the left of the triangle, not so much to the right. This line?
You have very sharp eye. And so in And the reason is because, this is contaminated by the very large resistance on this side because we measure on the whole layer. So if you flip, do the measurement, you drive electron and drive hole and open circuit electron, and that feature will show up. And other devices, when this edge is cleaner, we also see another line coming out of this. So only in this picture, I don't have that, but you should have that. Okay, so I think I'm done. So let me, yeah. So let me just summarize. So I hope I convinced you that this is a good platform to study dipolar exciton fluid. We've demonstrated perfect Coulomb drag up to about 20 Kelvin, and we've realized equilibrium triumph fluid. But then, of course, you should ask a question, where's your exciton superfluidity? The answer is we don't have that yet, but experiment, is on the way. There's some theoretical paper predicting exciton-mediated electron pairing for superconductivity, interesting pursuit. Can we put these excitons or trions in a lattice? Now we can study bosons and Bose-Fermi mixture in a lattice. And this is something, AMO community studies quite a lot, when they put on optical lattices. And one other thing I want to mention that, I'm not going to show you some experimental results, but this is also another question. So this is what people study in the quantum Hall regime exciton condensate. You have electron or hole. You usually, let's say, electron in both layers, right? And you turn on magnetic field, and you put into the half field, the Landau level. And then you can do some kind of transformation from electron to hole, and then you consider this exciton condensation problem. And in our problem, we have one layer is electron, the other layer is hole, and then we apply magnetic field. Is this the same problem or different problem? To me, it sounds like it's a different problem. It may look like in this case, you have magnetic field up for one layer and magnetic field down for the other layer. So this will be an interesting system also to study. So we have some results from this study. So far, it's like a competition between the excitonic insulator and the layer decoupled quantum Hall states. So you see interesting quantum oscillations. So with this, I would like to stop. If you guys have more questions, please feel free. Maybe, ideas, different directions to pursue, welcome. Yeah, so, okay. So, are you a theorist? I just want to make sure. That's my impression, okay? So we dream about detecting superfluidity. So let me ask the question differently. How would you detect this, in experiments, what would be considered as a signature of a superfluidity, okay? So one kind of a straightforward idea is to, okay, so now if we can flow exciton, right? So I have my sample here. If I can measure the chemical potential of exciton at location A, and then along the stream, right, I can measure the chemical potential of exciton at location B, and then I found there's no drop in the chemical potential. So this will give me some confidence, there is a supercurrent of exciton going on, right? And this will be a signature of exciton superfluidity. But of course, that's not enough, right? So you need to demonstrate coherence, how to do that. And that will be another experimental challenge. Just to make the measurement I described is extremely challenging. So I show you the cartoon picture, you can put the gates here, you can put contacts here, put contacts there, but in reality, if you want to put 4 pairs of contacts in your sample, this is more than 1 PhD thesis.
So in the drag experiment, if we just consider the ratio of the voltage and the drive current, so that's the ordinary resistance. Do you observe any signature for across the model?
Okay, I think I don't quite understand what you are asking. Maybe you explain this again. So you are talking about this experiment, right?
This
Yeah,
experiment.
yeah.
I'm thinking just
Yeah.
what is the ordinary resistance? Just the drive current.
Okay, so you say I measure resistance here.
Yeah, just this.
Like make it a 4 point.
Yeah.
Yeah.
And
So there is a finite resistance.
does it change abruptly across most?
I don't think this would be sensitive to more transition.
Because I'm thinking about whether
Yeah.
the mobility for
Yeah.
exciton are different from
Mobility of
electron. So whether, because to me, the mental picture is that
Yeah.
when you go across small transition, you start to add electron and holes, free electrons and holes, and they short circuited the exciton so that you don't see the drag current. That's my mental picture of the problem. So I just wonder whether you
see.
different mobility for
That's a good
exciton
point.
from-
We should examine this more carefully.
Yeah, so in quantum Hall bilayers, Eisenstein was measuring the zero bias peak in the tunneling.
Yeah.
Is this?
That's something we cannot do because we have a bias across the 2 layers.
So what would your
Signature for phase coherence, you mean?
Yeah.
I don't know yet.
There was also
Yeah.
you measured also dispersion.
Doing some kind of an interference experiment, maybe, build some kind of a heterojunction in plane, maybe.
You also measured dispersion of the Goldstone mode.
Yeah. Rotons, right? Those.
Not
Those
rotons,
are
but actually the sound mode.
some mode.
By putting on a magnetic field.
That's something we can do. Yeah.
In this experiment, how can I estimate the trion
Binding energy. Oh, this is just an estimate from the temperature dependence. That's the activation. Yeah. It's just an estimate. That's why you see huge arrow bars.
Sorry, I was a little bit discussed the continuous knot transition. So you show this parameter A is diverging. So how am I supposed to understand like microscopically what A is representing? That suggests that this is some sort of like that relates it to the phase transition.
So this goes back to the mechanism for fractional drag, right? So if we consider this is Fermi liquid, and that's derived from there.
Okay. I mean, maybe this is dumb, but I don't understand why. For the you're talking about the conductivity of excitons, right?
No, those are the uncoupled electron hole, and you drive one layer, and then the other layer, because of the Coulomb interaction, you have the frictional drag. I can point you to some reference. That's a good question. We have not seen the BKT transition. But from the picture of non-interacting bosons, you know, this paper. Yeah, from this paper, and you can see the BKT transition temperature is, you know, a few times smaller than the degeneracy temperature. And, you know, if you think this is some kind of valid picture, you know, the degeneracy temperature in our measurements is on the order of, you know, 50, 60 Kelvin, then we should be able to see this BKT transition already around the 20 Kelvin. But since we don't have, you know, a good probe at this point to show that there is, you know, probe of a superfluidity, it's still an open question experimentally.
Well, defining at 20 Kelvin.
20 milli eV, so that's room temperature. 25 is 300 Kelvin. Yeah, of course. You mean different material, TMD materials, or different? You're talking about Hall measurements.
No, I imagine some more material.
Yeah. Yeah.
Let's say you have some band with either electron or hole, put something that will form an actual.
Yeah. Mm-hmm. So this is a good suggestion. We are trying, you know, no result yet. Stay tuned.
What's at the BKT temperature scale in this problem?
No, in this picture is not interacting.
It's not.
Yeah.
While you have this picture up, can you say again the meaning on the left-hand side of T star and T star star, and how they might correspond to the right picture?
Yeah. So this T star is the estimated degeneracy temperature from the density, and that corresponds to this line. Okay. And this T star star is from experiment. You know, you just see this dome, right? That's the darkest color.
Oh.
Yeah.
Yeah, so near the continuous mode transition, what is the scaling of this accident resistance, tension scale? So you fit it using the AT square where AT divergence.
So that's on the metallic side, what we did.
Okay, yeah.
And the exciton binding energy goes to 0 if you want to draw what's going on in the other picture.
What is the scaling of this temperature scale?
Temperature scale of I don't quite understand what. So this, okay. So the drag resistance, you know, goes like AT square.
Yeah.
And this A is just the fitting.
Yeah. I'm just curious. At
the
continuous mode transition point,
the
MT square scaling is not applicable. So what is the scaling at this point? I mean, it must be T to some power which is less than 2. What is the power?
We probably need to discuss a little bit more. You need to educate me about what you are thinking about.
I'm just curious. I'm just trying to link it.
No. That's,
Yeah, but near the transition, the T square is small, right? So when you something is power load behavior, you need a large range to fit the power load reliably, but that's just not possible. So that's why the other side of the metallic side of scaling is very deep variable as we
close to the transition.
It's like, sorry. Is it possible to like extract the gap using some RNAs?
The gap we measured using capacitance, so I didn't put on the picture. If you look at the paper, it's there. Yes. But that measurement is less accurate, the error bar. And the reason is because when we do the capacitance measurement, you put an AC modulation, and that amplitude of AC modulation already limits how small gap you can measure. So very close to the transition is difficult to probe.
More like an open question. Do you have any intuitive idea about like realizing this experiment in 3D systems? I feel like just to scale up like this is not a good approach. As I said, in order to put full pairs of contacts on this one pair already, costs. I think this graduate student probably hates me. I don't know how many.
With you. I mean, just from the school, I'm just so impressed. Your vast, limitless imagination of what things can be done. I mean, even in the word. And, yeah, it's just like so incredible. What could have been done, and how many grad students if I asked them to do that, or etc. But then on top of that, oh, why didn't you make it? Oh, why
but once you come up with some kind of a deposition technique, like not by stacking, I feel, or crystal growth, maybe. Yeah.
Isn't it? I mean, any other questions? Love to hear this very
No.